Okay, so before the break, we have learned, give you a introduction about the functional data analysis. So now let's go to the first topic in functional data analysis called functional principal component analysis. So functional principal component analysis is one of the most important area in functional data analysis, and also functional PCA is also the most important tools when we do functional data analysis. So therefore, it is very important for us to master this tool and also understand how we can interpret the functional PCA results. Okay, so now let's start. So we have learned the principal component analysis in multivariate statistics. Okay, so basically here I give you one example. In the left graph, I show you two-dimensional data. Okay, so here we want to do the dimension reduction. So we want to reduce the dimensional data from 2 dimension to 1 dimension. Okay, so in that case, we definitely want to project the 2-dimensional data to the direction with the greatest variations. So in our case, in this graph, will be the direction indicated by the red solid line. So in this direction, the data has the most variations. Okay, so then we can project the 2-dimensional data to this direction, and we have 1-dimension data. Okay, so this is the dimension reduction technique. Okay, so so this is very convenient, and PCA is now served as also the one of the most important tools when we work on high-dimensional data. Okay, so just a little bit analysis about PCA. So basically, here, suppose we have a vector x. It's a vector of multiple variables, and we have their covariance function capital sigma. And then we want to find a direction u. U is also a vector, so we want to project the vector x to the direction u. So the projection will be the inner product between u and x. So for the vector space will be the u transform x. Okay, so this is the projection of the data x on the direction u. Okay, so then the projection u transpose times x, the variance will be u transpose times capital sigma times u. Okay, so our objective is try to maximize u transpose capital sigma u. And to make the u identifiable, we want the constraint that the length of the u equal to 1. So will be the u transpose times u equal to 1. The reason because if we multiply u by 10, then this u transpose capital sigma times u will become 100 multiplied by the original variance, right? So we can, if we don't have the constraints on the length of the u, this variance can be increasing indefinitely. So so here we constrain that the length of u had to be equal to 1 and maximize the variance of the projection. Okay, so when we do this, and we learned that in algebra, this optimization problem actually is equivalent to solve the eigenequation problem. So we learned that the u maximize the variance is the eigenvector of capital sigma, right? Okay, so this is a very important connection between maximizing the variance and the solve the eigenequations. So so there's also some terms in the PCA. So basically, we will first estimate the covariance matrix capital sigma by the sample covariance. So this xi here is a centralized vector. So we remove the mean of xi first. So the sample variance for the xi will be just the average of xi times xi transpose. Okay, so after we get this sample covariance, we can just take the eigen decomposition and we find the eigenvector u. So the eigenvector in u are orthogonal. So this eigenvector in u are called a principal component. And the D here is a diagonal matrix. Has each diagonal element will be the eigenvalue of the sample variance capital sigma. And so here the eigenvalues we write down as dk. So we can write down the ratio of dk divided by the summation of all dk. So then we will call that this ratio as the proportion of the variance is planned by this eigenvector u. So we order the element of the eigenvalues, and so then the case column of u will be called the case principal component. Okay, and then we will do the projection of the xi on the uk as the inner product of xi transpose times the uk as the case principal component score. So this will be the new coordinate in the space defined by the principal component. So these are the some terms we used as in the principal component analysis. So now let's go to functional principal component analysis. So FPCA, as I mentioned, is very important for functional data analysis. So you have to understand FPCA to do any functional data analysis. Okay, so this is very important. So basically here, we want to find some top K FPCs, W1T to WKT. So the capital K, the number of FPCs, typically it's very small. So we only need 2 or 3 FPCs. So this top FPC will summarize the major source of variations among multiple curves, XIT. So the curve XIT is project to the FPC scores SI1 to SIK. So the function XIT can be written as a linear combination of this FPC WKT, and the coefficient will be the FPC scores SIK. So you can see here, basically we're doing a dimension reduction. So we project the infinite function XIT to the finite FPC scores SI1 to SIK. As I said, capital K typically to be very small, so K will be 2 or 3. So this FPCs W1T to WKT will be estimated as a linear combination of the basic functions. We typically will using B-splines, and the shape of the top FPCs are very simple. So now let me give you one example. So here, this is to show you the number of eggs laid by 50 fruit flies over 25 days. So here, the number of eggs for each fruit flies laid over 25 days will be one curve. Okay, so now we have 50 curves show you in the graph. Okay, so you can see these 50 curves are pretty messy, right? And so our objective is to explore the major model variabilities among these 50 curves. So here, this is some notations. Suppose we have n curves, x1 star t, x2 star t to xn star t. We have to first remove the mean curve first, okay? Because here we mainly focus on the variations among these curves. So basically, we will calculate the mean curve, mu t, by taking the average of all n curves, and then we will remove the mean curve mu t from the original curve, okay? So we call it pre-processing. So this is the function xit. We call it a centralized curve, okay, after removing the mean curve. So what we will do is that suppose the first LPC is W1T. So then we will project the curve xit to the first LPC W1T. So the projection will be the inner product of these two functions. So in functional space, the inner product will be the integral of the product of W1T multiplied by xit. And this projection will be called the first LPC score, S sub I1. So our objective is to maximize the variations for the first LPC score. So because here, our xit is a centralized curve after removing the mean, so the mean of our the LPC score, S sub I1 will also equal to 0. So therefore, the sample variance of S sub I1 will be the sum square of this first LPC score, S sub I1. So we want to maximize the variance of the LPC score, or we want to maximize the summation of square of the LPC score, S sub I1. And so similarly, to make the LPC to be identifiable, we will put the constraints that the integral of W1T square will be equal to 1. Okay, so so here the first LPC W1T represented the strongest and most important mode of variations in this N curve. Okay. Thus, so here we can also work on the second LPCs, W2T. Okay, so we can calculate the second LPC score S sub I2 by project xit to the W2T by doing the inner product between W2T and xit. We have the integral here. And then we maximize the variations for the second LPC scores. So the variation of the second LPC scores will be equal to the summation of square of the second LPC scores. And we will put the constraints that the length of the second LPC W2T equal to 1. So the integral of square of W2T will be equal to 1. And the inner product of W12T and W2T, W1 of T and W2 of T will be equal to 0. So the W1T and W2T have to be orthogonal. Okay, so we want to find the second strongest and the most important modal variation in the N curve W2T, orthogonal to the first strongest modal variations, the W1 of T. So similarly, we can obtain the rest top capital K FPCs W3T to WK of T. FPCs are orthogonal to each other. And so then this XIT is project to the FPC scores SI1 to SIK. And also we can write down the function, the curve XIT as a linear combination of these FPCs WKT, and the coefficient will be the FPC scores S sub IK. So here we show the top 2 LPCs for the Metafly data, the fruit fly data. We have 50 curves, and so we do the LPCs, LPCA, and we find these the top 2 LPCs. I will show you later how we do the estimation. So you can see that although the original 50 curves are very complicated, these 2 top LPCs actually have a very simple trend, right? So these top 2 LPCs actually are estimated by B-spline basis functions without making any parametric assumption, and it explains the top 2 LPCs explain the 91.6% of the total variations among the data. The top 2 LPCs have a very simple trend. You can see here. Okay. So now let's look at the interpretation of the FPCs. Okay. So in the past, I found that actually it's pretty easy for students to master how to do the LPCAs. But the most difficult part is to do the interpretations. Okay. So therefore, I want to emphasize how to do the interpretation for the LPCs. So here, this graph shows the top 1, the first LPCs, W1 of T, and so it explained around 62.2% of the total variability, and it is positive over the whole time period, right? Okay, and so this is to show the FPC scores. I find that it's easier to understand or interpret the FPC by looking at this formula, how we calculate the LPC scores. Okay, so you can see that FPC score S sub I1 is the inner product of W1T and XI of T. Okay, so if you look at this formula, then how do we interpret the first LPC scores? Any ideas? Any volunteer to tell me how you will interpret the first LPC or the first LPC scores? Okay, so here, this W1T is positive over the whole time period, right? And if you look at this formula closely, you will see that W1T, the LPC score, actually is the integral of XIT multiplied by W1T. So in other words, the first LPC score can be treated as the weighted average of the curve XIT. The weight is the FPC W1OT, right? If you look at this formula closely, right? So now we know that the first FPC score is the weighted average of the curve XIT with the weight defined by the LPC1. And so you can see here the weight LPC1 is the highest around day 8 and lower in the lowest in the bottom around day 25, right? So this is how we interpret the first FPC score. So the first FPC score is the weighted average of the number of eggs laid by 50 fruit flies over 25 days, okay? With the highest weight around day 5 and the lowest weight around day 25, right? So the first FPC score is just the weighted average of the curve. Sorry, I want to find the fruit flies curves. So here you can see here we have 50 curves, right? So you can see here on the first LPC put the most weight around the day 5. The reason is that if you look at the curve vertically, you can see that these 50 curves have the largest variation around the day 5, right? And if you look at the curve vertically, you will see that the variation among these 50 curves has the lowest variations around day 25, right? The reason is because the fruit flies decays over time. So when they reach the day 25, the amount of eggs, they will lay less eggs now, right? So the variation around these 50 curves will be the smallest around day 25. So you can see here, our top LPC will be able to automatically find out where to put the highest weight, where to put the lowest weight, right? So this is a beauty about the LPCs, okay? So the first LPC will be weighted average, and it will put the highest weight on the curve with the largest variations, okay? So this is the first LPC interpretation for the first LPC score. Is this clear? Any questions? Okay, so now let's look at the interpretation for the second LPCs. Okay, so the second FPCs is planned around 29.4% of total variability. And so we can see that the second LPC is negative before day 8 and positive after day 8. Okay, so recall that for the first LPC, it is positive over all the 25 days, right? Okay, so again, I find it is easier to interpret the second LPC scores by looking at the formula here, how we calculate the second LPC scores. Okay, so any volunteer to tell us how you would like to interpret the second LPC scores? I will wait 30 seconds. You can think about how we interpret the second LPCs. Okay, so 30 seconds. Any volunteer? Okay, so here, as I said, we can interpret the second LPC scores by looking at this formula, right? You can see that the formula is the same. So the second LPC score is still the integral xit multiplied by W2T, right? So the second LPC score can be viewed as the weighted average, again, on xit. And the weight is defined by the second LPC, right? But here, the weight W2T is negative between day 8 and positive after day 8. So in other words, xit will multiply by a negative weight before day 8 and positive weight after day 8. So therefore, we can interpret the second LPC score as the change of the number of eggs laid by the 50 fruit flies after day 8 in compared to before day 8, right? Because after day 8, it gets a positive weight on the curve. Before day 8, it gets a negative weight on the curve, right? So if you think about if W2T is constantly 1 after day 8 and a constant negative 1 before day 8, so then it will be the average of the curve after day 8 minus the curve of xit before day 8, right? Okay, so here just we have a continuous weight. Okay, so this is how we interpret the second LPCs. Okay, so the second LPC score will be interpreted as the change of the laid eggs. So for example, if you think about if one fruit fly had a relative small change, has a small decay on the number of eggs laid. So it may have very few eggs laid in the beginning and very few eggs laid in the end as well. So then for this curve, it will have a big first LPC score because the average is small, but it will also have a small second LPC because the change is small, right? So so here I want you to understand that so about these two LPCs. The reason I spend a lot of time to do this because in reality, I find that 90% of applications, the most applications will have the same trend for the first LPC and the second LPC. So for most applications, the first LPC will be always positive over the whole range. Okay, so standing for that the first LPC score will be the weighted average of the whole curve. Okay, the weight will happen, the weight, the height of the weight will, the peak of the weight will change at a different time depending on the applications. Okay, but the weight function FPC1 will be always positive. Okay, and for the second LPC, I find in most applications, the second LPC will be always negative at the beginning and positive after some time. Okay, so in other words, the second LPC will be always interpreted as the change of the curve after some time. Okay, so the change time, the time where LPC2 will go from negative to positive will be different from different applications. But for most applications, the second LPC will be negative at the beginning and positive after. Okay. Another thing I want to mention is that for the LPCs, it is identifiable up to a sign. So in other words, you may get the second LPC positive at the beginning and negative in the later stage. In that case, it's fine. You can multiply by -1. You will still get this trend. Okay. Or sometimes you will get the first LPC to be negative over the whole time range. In that case, you also can multiply by -1. You will get a positive LPC1 over the whole time range. Okay. So this is how we interpret the first LPCs and the second LPC. Any questions?
Yes, I have one.
Yes.
So it's really interesting here. I want to know why the first FPC1 is always the same sign and the second one changes.
Yes, this is a very good question. Actually, I don't know myself either. So this is kind of the observations after doing FPCA for many applications. I don't know why it is always first LPC always positive, second LPC always, first negative and then positive. It will be very nice if you can show it, right? Yeah, I think there must be some mathematical proof to do it, but I don't know why this happening. Yes. Yeah.
Thank you.
Yeah. So one reason maybe because that the second LPC have to be orthogonal to the first LPC, right? So if the first LPC to be positive over the whole range, then the second LPC had to be negative in some range and positive in some range in order that the second LPC multiplied the first LPC will be equal to 1, right? So that's one incomplete answer to this. Okay, but I'm still don't know why the first LPC has to be always positive. I guess maybe in nature, when we look at the variation in the curves, I think the first most variations is the mean, right? And the second most featured for the data is the variance, right? So I think in terms of the curve, the second LPC will serve as the variance of the curve over the time. Okay, so the first LPC will be the mean, the second LPC score will be the variance of the curve. Maybe that's the reason. Yes. So I remember like in some when we do the machine learning for curves, if you want to find the features from the data, I will see that 90% of times the feature of the data will be the average of the data, right? And also the second feature will be the variance of the data. So I think maybe that's the reason why the first top 2 LPCs, one is always positive, the second one is a negative and a positive. Okay, yeah, but still I don't have the mathematical proof for this.
Thank you.
Yes. Welcome. This is a very good question.
Sorry, I have another question.
Yes.
Do you think it is possible to use to replace the first 2 pieces with the area under the curve divided by over days, and also the second use the slope at 8 days? Just replace it.
You mean to interpret the LPCs?
No, like you use in the model. Here you have the two pieces.
Yes.
Do you think it is possible to replace the first pieces with the area and the curve divided by the over days, and also the second pieces with the slope at the specific time?
Okay. Yes. Yeah. So this is a very good question. Very good idea. Yeah. So I will see. You definitely for the, you can see that for the first LPC, actually I think Xiaoyang mentioned a very good point. So before I interpreted that the first LPC as the weighted average, right, of the curve, because this is the integral xit. But Xiaoyang actually reminded me that this integral of xit can be also viewed as the area under the curve xit, right? So in other words, so we can interpret the first LPC scores as the weighted average of the curve. We can also interpret it as the area under the curve, weighted average under the curve, right? Yes. Yeah. So yes, it is possible. And yeah, so for the second LPC scores, as again, this integral can be viewed as the area under the curve. So so I'm not sure like whether we can look at the slope of the around day 8. So definitely, for the second LPC scores, let me go to the data. Basically, the second LPC look at the change, right? How the curve go from the beginning to the end. So I will see that Xiaoyang is correct that actually the second LPC can also be looked at as the how quick the change is, right? In other words, is the slope of the curve. So I know, like for example, if we do a linear fit on these curves, so the change will be the slope, right? So in other words, it is fine, if you think to just look at the slope, if we fit a linear curve from linear line and look at the slope of the linear line, I think probably it will be very close to the second LPC scores. Yes. Yeah. I guess this is how we often do in the longitudinal data, right? So we will look at
Yes.
slope. Yes. Yeah.
Instead of using the pieces, we use the area and the curve and the slope. So instead of, I think it's the same idea.
So sorry, like Xiaoyang, where you look at the area under the curve? I want to know. You're very interesting.
So this is a project cooperate with my mentor. The paper is about the LGL cholesterol.
Yeah.
Yes.
Okay, I see. Okay, yeah. So yeah. So like if I will be very interested to read your paper and yeah yeah. So when you're ready, can you send me the paper?
Yes.
Okay, that'd be great. Yeah. I actually I'm very excited to hear these connections. Yeah. So you see, like in longitudinal data, like we always doing this linear trend, right? We look at the kind of with the intercept, right, and the slope. So somehow the intercept will be the average of the curve, right? Because we'll adjust the intercept, and the slope will be the change of the curve. So in other words, the intercept will be the first LPC scores, and the slope will be the second LPC scores. Yeah, this is a very cool. I like these connections. Yes.
Okay, thank you.
Thank you. Yes. Yeah. Any other questions? Okay. Yeah, this is very good. I find more insights about these LPC scores. So you can see here, actually, like you can look at kind of these LPC scores is kind of like fancy versions for the mean and the variance, right? It kind of will have defined this weighted average. We define this weight instead just look at the average, right? And for the thin LPCs, instead look at the slope, we look at this continuously weight W2T. Okay, so maybe you can look at it as kind of more fancy or detailed version for the average and the change. Okay, cool. Okay, so now let's continue and yeah. So any more questions before I continue? Okay, great. Okay, let's look at the more details about the FPCs. So as I mentioned at the beginning, that yeah, I think now is 7:40, and I think maybe this is a good time to stop. So now we actually have going 50 minutes. Okay, so I also want to give you some time to think about the interpretations because it's very important for you to understand this. Okay, so let's have a 10 minutes break. Okay, so now it's 10:41 in New York time, and so